So thanks for having me. Thanks for sticking out to the end. Thanks for coming to this this slot. What I'm going to do, I'm just going to really talk about the stuff I've been mucking about with since the last time I spoke at CodeMesh, I think maybe a couple of years ago. I'm working on this programming language called Idris. So Idris is a pure functional programming language. It supports this concept of type-driven development, so kind of by analogy with test-driven development. We come up with the types first. We write a program by kind of repeatedly refining our program and the types until we get a good understanding a good enough understanding that we can model the problem in types. And I got to a point with developing, or coming up with examples for Idris and writing programs in Idris, where I thought I was running into that kind of problems in the implementation, and I found that I needed to do some pretty hefty re-engineering of the core. And I thought, well, if I'm going to do some hefty re-engineering of the core, I might as well just start again. And if I'm going to start again, what programming language might be my first choice now? So I thought I'd have a go at developing in Idris. And as a result of that, Idris has got a lot better, because if you, like, there's always a question of when is it a good idea to make a programming language self-hosting? There's always this gag of, the question at the end of the talk, does your language do anything other than implement itself? It's like, well, yeah, okay, it's not necessarily great that it can only implement itself, but if it can't even implement itself, then we have a problem. So essentially, I've been trying to make Idris good enough to implement itself, and what I'm going to show you today is the result of those labors. Now, I didn't just want to re-implement it again in exactly the same way, because, you know, I made a few, I think I made a few mistakes in language design, a few mistakes in the choice of methods for implementation, and I thought I'd be original this time and make a whole new creative set of mistakes. And I don't actually know what the new mistakes are yet, but it's going to be enormous fun finding out. Right, so just to say what the talk is all about, introduce Idris if you haven't seen it before. So I think two important things. Firstly, I like to call it Pac-Man complete. Rather than Turing complete. Turing completeness isn't really a very interesting property of a language, because lots of languages are Turing complete, but you still can't implement Pac-Man in them. So it's really, can you implement Pac-Man in it? That's really what I'm looking for here. And that just means, like, can I interact with the outside world? Can I explain what's going on with resources as the program is running? I can't show you Pac-Man yet. I actually did some investigation, and there's all kinds of trademark issues. So I'm not even sure that it is Pac-Man complete in that sense because of the trademark issues. Anyway, another key feature, I mean, the most important feature is that it has first-class types. So when we're teaching functional programming, sometimes what we say, or sometimes what I say to audiences, or to groups of students, is the key thing about a functional language is that functions are first-class in a functional language. Well, that means you can assign functions to variables, return functions, compute functions, and so on. So by first-class types, I just mean exactly the same thing for types. I can assign types to variables, I can pass types to functions, I can write functions that compute types, and so on. And the other thing that I want to highlight as I'm going through these introductory examples is the key new feature that I am starting to kind of understand, finally, which is linear types via a core language developed by Conor McBride and Bob Atke over the last year or so that they call quantitative type theory. And the basic idea behind quantitative type theory is that every variable has an annotation, or every variable binding has an annotation with it that says how many times it's used. There are zero, it's basically 0, 1, or many. So there are two interesting numbers, 0 and 1, and then there's all the other numbers. And I'm going to show you how that impacts programming. So yeah, if you've been to one of my talks before, you know that I generally like to have a few introductory slides and then just get on with the live demo. So that's the slides out of the way. And I'm just going to get on with the demo. So is this all right for font size at the back? Are you okay reading that? Nodding? Good, great. So I'm going to spend a little bit of time just kind of really hammering home the fundamentals. So this example I'm going to show you it might seem a little bit trivial, but it is a little bit trivial. But if you get what's going on, you have really got the essence of first-class types. So I'm glad you mentioned Go, actually, because I brought a Go book with me. This is my favorite book on Go, Go the game. It's called Lessons in the Fundamentals of Go. And it's my favorite book on Go, largely because it's my favorite book on anything. And the key message of this book is not really about Go. It maps to a lot of things, which is that, oh, some thumbs up. You play Go? We'll have a game later. The key message of this book is it's no good understanding the complicated things if you don't understand the absolute basics first. And time and again, you see that in so many different contexts. He illustrates it for things like baseball and cooking and so on. So I'm going to talk about the fundamentals of first-class types. So what we do in type-driven development, we start with the type. So I've written a few type signatures here. So type is the type of types. I'm doing all this. I'm going to be doing all this interactively using Atom. So I've got as far in implementing Idris 2. I've got as far as implementing the editor interaction protocols. I guess in theory this would also work in Emacs, but I haven't tried it yet. So what we do is we write a type signature, and when we write function definitions, so this is a purely functional language. It's a little bit like Haskell. So just by show of hands, anyone know Haskell? That's most of you. That's fantastic. If you don't know Haskell, the syntax here might be a little bit strange, but just try to grasp the concepts and don't worry too much about the syntax. But the important thing is we define functions as a kind of collections of recursively defined equations. So we give some patterns that the inputs can match and then what they map to. So here I'm going to write a function that takes some Boolean flag as an input and it computes a type. So what do? I hit Control-Alt-A and it gives me the first candidate definition. And the key concept for this type-driven interactive approach is this concept of holes. So this int or char RHS thing you see here, this is a valid bit of syntax. It's a hole, and if I ask for the type of a hole, it tells me what I have available and what has to go in. So kind of unsurprisingly, we have this flag is int, and we have to compute something that is a type. Okay, so I have a few, in this kind of interactive approach, there's a few moves I can make. So adding a candidate definition is the first move I could make. Another move I can make is, that's not a deliberate Go analogy, by the way. Another move I could make, I'm kind of forced by the move here, is just asking for the possible values for isInt. So if I hit Control-Alt-C for case split, it will give me the possible values of that variable, and I'll just fill in the right-hand side. This will be an int if it's true, and this will be, let's make it a char if it's false, because that's the name, after all. Right, so where do you use these things? Anything that computes a type, I guess the natural place to use that would be anywhere that requires a type. And sort of places where you require types are function type signatures. So I have this little function called showThing, and the idea of this function is it will take something of some type as an input, and we'll render it as a string. And this first flag isInt will tell us what the type of the second thing is going to be. You get the idea? I'm making sense? Good, good. So let's add a candidate definition. Again, it's always a good idea to look at the type of the hole. Whenever you get a new hole generated, look at its type, see if you can learn anything from it. Type-driven, after all. So check the type of this hole. So we have something called isInt, which is a bool, and we have something called x, which is something else. This is like a function. So it kind of suggests that the only reasonable thing I can do if I want to look at x, if I want to learn anything about x, I have to look at what this flag isInt is. So I'll do a case split on it, and if we check the types of these resulting holes, showThing RHS1, we'll see that it's refined the type of x to be int in this first case, and in the second case, showThing RHS2, it's refined x to be type char. Okay, so what's happened here is that, this is a function that we don't know what int or char is going to give us until we kind of run the program. On the other hand, at compile time, we can reason about what's going to happen next when we do get that value. So I guess I could finish this off just for the sake of actually showing you how a program runs. So let's print int plus show x, and let's put char. So show just converts anything to a string. It's kind of like Haskell. If you know Haskell, this will be vaguely familiar. So let's, I didn't have this quite set up. I call this Blodwin, by the way. So did any of you watch Ivor the Engine? Oh, that's a very disappointingly small number. You must go and watch it immediately after this talk. It's a fantastic sort of 70s series of cartoons about a steam engine. And Idris was a dragon who hatched out of Ivor the Engine's boiler. And I can't remember exactly what led to that being the name, but I'm kind of stuck with it. Anyway, Blodwyn was one of Idris's sons. And I really only call this Blodwyn rather than Idris 2 to keep them distinct enough in my head. I'll probably give it a sensible name eventually, Idris 2. So we'll start up on this little program. And there we are. It's type checked OK. So I don't know what you're laughing at. So we can try running that, and true required an int, so let's give it an int. So, like, why have I gone to such lengths to show you this simple function that just prints a string? Well, and you might think, why would I ever do that? Well, if you've ever written in C, you've probably used printf, and this is really just a really, really minimized printf. So I have a slightly less minimized printf to show how you can use these techniques to build more interesting types. So, you know, if I check the type of printf, %d, %s, it's computed that I need an int and a string. So, you know, it's always worth showing you what happens when there's, let's have a, it's always worth showing what happens when something goes wrong, just to see what the error messages look like, because someone always asks at some point, so I'll preempt the question. It's, that was actually a really bad choice of yeah. Type miss. We'll see a few of these things, because I'm literally, it's like 2 weeks old code, more or less. So you know, just as a mismatch between string and int, because we got the format string wrong. So that's the gist of it. That's what first-class types is all about. We are writing functions which compute types. Also, while writing functions that compute types, we can, that means we can have, functions compute types, meaning that kind of types are values in this very real sense. We can also put values in types. So we can use information about one part of the program to inform other parts of the program. And the classic first example of this that you always see in a dependent types talk is the vectors. And this is no exception. I'm going to show you how Idris does vectors in the new version. So just to give a bit of background, there is a type of natural numbers, so unary natural numbers, 0 or successor of another natural number. Now this is, it's not the most efficient way to represent numbers on a computer, but we're going to do it anyway, and I'll show you in a moment why that's not a problem. So the nice thing about representing numbers in this way is they have this kind of nice mapping to what's going on in lists. So 0 kind of corresponds to a nil, and successor corresponds to a cons. So when you have these two things that go together, plus on natural numbers and say append on lists, is that a coincidence? Well, it's not really a coincidence. These really are two similar structures. They have similar behaviors, and we should start exploiting that link between these structures. And once you start writing more precise types, you start seeing more of these relationships. So we'll define vectors as I said, you know, 0 has this nice correspondence to the empty vector. So here's the empty vector. It has length 0, so z for 0. Here's the non-empty vector. So if I have a thing and I have a vector of k things, that gives me a vector of successor of k things. So we'll just work through again, just write a type, define the function, and refine it as we learn more about it. So I'll add a candidate definition for append. We'll look on the right-hand side here, and you'll see these mysterious zeros. So this is a new thing in Idris 2. This is where the quantitative type theory is coming in. So this 0 means that we can talk about what M, A, and N are. It is valuable compile time information to know that M is a nat, A is a type, and so on. But we really don't want these in the program at runtime. The program we run is only about the vectors, nothing to do with these numbers and these types. So this 0 means that we can talk about it, but we can't have it at runtime. So the rule is, the strict rule is, if you don't bind it explicitly in the type, so here N, A, and M are implicitly bound, so I don't have an explicit kind of for all binding or lambda binding. If you don't explicitly bind it, it will be considered not used at runtime. Okay, so to write append, as you know, you're mostly familiar with Haskell, you know that you pattern match on the first argument. So I'll case split on x's and see what cases we get. It's always a good idea to look at the types of the wholes. So this right-hand side says, well, the only thing I have available to use is this y's, which is a vector of m things. I need a vector of m things, so there's only one thing that works here. So I'll say to the machine, just search for the thing that works. And it found y's, that's good news. Pleasingly, if you do it on this other case, again, there's a few things we can use. I've got a vector of m things, a vector of k things, and I've got another a, and I need a vector of 1 plus k plus m things, which is a pleasing coincidence. There seems to be a quite natural way to glue that together. So I say to the machine, have a look. There you go. So this is still a little bit disappointing. Like, somehow all of the moves I made were forced there, weren't they? Like, it was like I k-split on a thing, I see what happens, I do a search. So, you know, if all the moves are forced, maybe the machine can help you a bit more. So what I do is I hit Control-Alt-G, and it's like they're all forced. So there you have it. So we do a similar thing for zip, or zip with. So you know zip, the idea with zip is that you have a list of things and a list of things and you kind of bring them together. And I guess, well, I'll do zip rather than zip with. So we've got a vector of n a's, we've got a vector of n b's, and we're going to make a vector of n pairs of a and b. So I'll do it slowly. So we create the candidate definition, match on the first, we'll pattern match on the first thing. So, and we'll look at the types of the holes. Always a good idea to look at the type of the holes. So zip RHS1, we'll see that what we now know about y's, because these two things were the same length, so we've made this explicit in the code that there is a relationship between these two inputs. We should get some value out of that. The value we get out of it is, once we've looked at x's, we at least know something about y's. So if I try to do a case split on y's, it's not going to give me the non-empty case because there isn't one. It's not valid. So if I do that case split, I only get the one possibility. In the second example, if I do the case split on y's, I only get the one possibility. And I didn't really need to bother doing that because, again, all of the moves are forced. We'll just look for the deposition of zip. Zip with is the same as thank you, but you have no idea how embarrassingly simple the code that does that is. The value you get when you put a bit more in types and you just say to the machine, search, you've cut out so much of the search space that, like, this literally took an afternoon. And I thought, it can't have been that easy. That's just embarrassing. It can't have been that easy. It was. So zip with is the same as zip, but you have any function rather than pairing. So, yep. We get zip with. So that's quite nice. Now, you would be forgiven for thinking that I just picked these because I know they work. And you would be right. Of course I just picked these because they work. However, it's worth thinking about the reason that they work. The reason that they work is that we identified that coincidence between lengths and lists. So we can just try to exploit that coincidence and get the machine to exploit what it knows about types. I'll give you a couple of quick examples of the kind of situation where this does work, just to give you a little bit of a feel for it. And I'm not going to give you examples of the situations where it doesn't work, maybe one or two, just because that's every other situation. So the kind of thing, like you could take advantage of parametricity. So you're familiar with the notion of parametricity? So this idea that if something is parametric, then the definition cannot depend on that parameter. No matter what the parameter is, the definition looks the same. So here we've got uncurry, which is given some function that takes an a and a b, convert it into a function that takes a pair of an a and a b. And finds that, because there really is only one way you can do it. Similarly for curry, there really is only one way you can do it. This select thing is a little bit more fiddly, so this is like a bit of tuple mangling. So the kind of situation where this is useful is if you have a little bit of annoying plumbing to do. Like when you're writing programs, you have annoying plumbing to do sometimes because the author of an API is giving you a pair and you wanted the first thing or vice versa. So maybe you run a function and you pull some things out and it's just all fiddly and boring, and why can't the machine do that for us? Well, the machine can do that for us. Another situation where you might want to do this is a little bit more complicated, but this is something that genuinely happens in the implementation of Idris 2 quite a bit, is maybe you want to explain some relationship between one list and another list. So this is maybe, I just hacked this up this morning, so I haven't really gone into any depth on this, but it's kind of a way of doing extensible records. So I've defined a type that says, well, I have a list, I have some strings, they're my keys, and each string has a type. So I've defined a record here. I put a cricket reference in for Sean. So there's a name field, there's a number of wickets field, and this is kind of like a list that a list with where the types tell us what the types of each element in the list is. So the sort of things that you might need to do with this is projecting values out of that list. And to project values out of that list, you need to have some kind of evidence that something is the type that you're looking for. And generally what you do is you'd write a predicate that says, this has key says, the key, this string in this list maps to this type. So it's almost like a function in a way, kind of a prologue-y type function where we're stating a relationship between three things. So if k comma tie is the first thing in this list, then k has type tie. So I've kind of explicitly stated that function. And if k has the type tie in the rest of the list t's, then it also has the type tie in a slightly bigger list. And we've kind of already written the function that projects the type out of the list. And when it finds that point in the list, there will only be one thing of the right type. And it's kind of annoying that we also have to write the function to do that when we've expressed in the type precisely what's going on. So with this machinery, there you go. It's basically it's looking at what I put in the type, and it said, well, there is only one way to write this function that projects the thing out of the field. Okay? I think that's pretty cool, if I say so myself. It's really satisfying somehow. I spend a disturbing amount of time just implementing zips and appends, because it's lovely seeing it do that. It's almost, yeah, I don't know. It's a hobby, you know. Right, so that's the machinery for generating programs. We've seen a little bit of quantity. So you've seen this zero annotation in the context when we're looking at holes. But I said that there were three interesting numbers, 0, 1, and many. So here's an example of one. So this, if I was the sort of person who made slides, I would have put this on a slide. This is the important intuition. So if you see a type signature of this form, so I don't know how readable that is in that color, but it's basically it's a digit 1 next to the variable name in the type declaration. So if I have something that says f is, I'll move the mouse pointer out of the way. If I have something that says f is a function from a to b, and there is a 1 annotation on the x, that means that if f of x is used once, then x is used once. So it's still possible to be in a situation where f of x is used lots of times if that's in a valid context. But if you're in a situation where you know f of x is used exactly once, then you also know that x is used exactly once, which means you can say things like, well, it basically means that f is only allowed to use x once. So that's ruling out these it's ruling out these unfortunate things we don't want, like DUP. So if I try adding a definition for DUP, and let's say, well, we know it's a pair. So okay. Actually, maybe I should show you what happens when the machine can't find a solution. It says in tiny letters, which I don't know how to increase in this mode. It says can't find a definition for main.dup. If I took this 1 out, then it would be fine. But I've given it this additional information that x is to be used only once. So I could try writing it, and I'll put another hole in. It's like, well, it's definitely a pair of things. We know it's a pair of things. If I look at the type of help here, it says, well, you've got 1x, so you can use that. If I look at the type of .rhs here, then again, I've got 1x, so I can use that. Great. So I'll use it here, and look at type of .rhs, and nope, I can't use it anymore because I've spent it. I can still talk about it. We can talk about, the glorious distant past when we had an x to use, but we can't use it. And again, this is a question some people sometimes ask, because on the assumption that the type checker is going left to right, do we get a 1 if I check the type of .rhs? I'll give it another name just so it's visually obvious. And nope, can't use it there either because I've used it somewhere else. Yeah, let's get rid of DUP because it's annoying. So the other sort of thing you might want to express is to say that we have a thing and we don't want it at runtime, but we want to have it in the type for whatever reason. So this function, bad not, imagine I'm trying to write a function by pattern matching on B here. but I've said that B is erased. So if I try to pattern match on it, if I try to case split on it, it says no valid case splits, again in a tiny font. Well, there are no valid case splits. I could persist and say, well, I know better than you. I'll try it. And it says, what did it say? Oh, that's interesting, because I didn't save it. So it says, again, you can't read this, I'll read it out. It says, can't match on false, erased argument. So it's a way of being explicit about what we want to talk about at compile time, but what we want to be sure is not used. Right, so 0 and 1 allow us to talk about a little bit about resource usage in programs. There's all sorts of interesting ideas that this gives us, like maybe you could start representing state machines in type. So if you're at Hillel's talk, you'll have learned all about state machines and state transitions, and it's a really good idea to think about the spec and what happens when you turn the spec into code. I think there is a gap that we should really start looking at of taking TLA plus and type systems and seeing how we can use them in a complementary way. So I think sometimes I write types that do like these interesting state transitions, and I think, well, I'm not actually sure my state machine is right. If I could feed my type to a model checker, maybe it could tell me things about my type. So this is the sort of thing you can start doing when you start being able to say, when you start only using something once, it means you can start tracking usage through a program, because once you've spent it, you can't use it again. You really can refer to external things that way. But there are other things you can do. Like this annotation of giving the number of usages gives us some additional information that the compiler can use when it's helping us to write the program. And I often say I like to think of the machine not as a thing that checks my code, but like my lab assistant. So writing down the type is like saying, hey, this is what we're going to work on together today. We'll kind of do some pair programming, me and the machine, and as long as I give the machine some more information about what we're going to do, the machine can help us out a bit more. So this is an example. I'm going to show you an example of that happening that has nothing to do with kind of performance effects of linear types, nothing to do with state machine tracking, just something where we give a bit more information. And it's my other favorite introductory program, matrix transposition. So I'm going to do take the vectors that we've looked at, and we're going to take an n by m vector, so basically a matrix, an n by m matrix represented as nested vectors, and I'm going to turn it into an n by n vector. And we used to do this to our undergrads. We'd say in Java, transpose a linked list of linked lists, because I don't know, we hated them or something. We don't do it anymore. So I'm going to do this with vectors, and I'm going to use the type information to help out a bit. So it's the usual thing of generate a definition, do whatever. I mean, I could try Control-Alt-G to see what it does, and yeah, I can't find a definition for that. It's a bit tricky. So we'll work through it step by step, see where we end up. So add a definition, and the only real choice I have here is to pattern match on our matrix. So I'll pattern match on the matrix, and in this first case, transpose RHS1, what does it tell us? It tells us we are looking for m copies of the empty vector. So we started with an empty vector of vectors of m things, so we're going the other way around. We need m copies of the empty vector. And when things are a little bit complicated, what I like to do is just rename the hole and press a button to turn that hole into a top-level type. So it's just a kind of a way of pulling out local definitions or helper definitions. This is a case of the machine has this information. So when I put that whole query empties, I know I need a helper function. The machine knows what type it's going to be. And if the machine knows what type it's going to be, why doesn't it fill in the code for me? There's a general principle of the interaction mode that I'm aiming at. We're not really there. Well, we're not even close. General principle should be, if the machine has some information, it shouldn't keep it to itself. There should be a way of getting that information out into your program. Sometimes people ask me about the language server protocol. I don't know if there's anyone here who does any kind of development on or with the language server protocol, but if you do, please can I have more features that allow me to extract this kind of information? So because every language could use this. Every type language could use this. Anyway, so thank you. Yes. So I could try writing this. Does anyone see what the problem's going to be? By the way, what's that? I need m at runtime. I'm going to run into trouble here. I could try generating the definition. It's not going to work. So let's undo that. Somehow I need to say to the machine, I have discovered in this process of editing that I need M. So what I'm going to do is I'm going to tell it that I need M. So I've now written an explicit binding for it. It's still going to be used implicitly, but I've written it down. And the fact that I've written it down means that it's in scope. So if I lift this out now, it's passed through M because it's noticed that I need it. And I'll just generate that because it's easy. Right. So the other case is the recursive case. Oh, I say the recursive case, the non-empty list case. It's always a recursive case. The only thing I can reasonably do at this point is transpose the smaller vector and see what happens. So we'll check the type of that, and oops, I've got to save it. Oh, thank you. I put these in just to show that it's not a video that I've practiced miming along to. So what do we see? We've got a transposed vector, which is m by k. We're trying to make an m by successor of k vector. We've got a vector of k thing. So sort of what we need to do is put the corresponding elements of x's onto, the corresponding elements of x, the vector of m things, onto this vector of m things. It's kind of like, imagine we've got if I had a whiteboard, I'd draw it, but imagine it's like a cube, and I've turned the cube round, and somehow I have to rotate the bit I've sliced off the cube onto the top, if you can visualize that. So I guess what I could do is just the same again, like lift out a helper function and generate it. And it does actually come up with something, but that's almost certainly not what we want. It type checks, but if that's going to be a thing that rotates a thing onto the top, no, it's not. In fact, I've tested it. It's not. It does some nonsense. I think it actually doesn't terminate. I haven't written the termination checker for this yet, and I think probably it should only find things that terminate. So I'll undo that and think, well, the question we should ask is there something we know about this problem that we haven't told the machine? And there's a few things. I mean, one is that if we transpose twice, we'll get the original, but that's kind of a hard thing to express. And given that I've been banging on about numbers, there's probably a clue in the thing that we haven't told the machine that would be useful. Like that matrix there, we're only going to use it once, aren't we? Like it wouldn't make sense to transpose more bits of the vector as we go. So what I'm going to do is say, right, I'm only going to use that matrix once. If I now check the type of transpose helper, we see that, yes, we can talk about the glorious history of x's when we hadn't transposed it yet, but we can only talk about it. We can't have it. So now if I hit lift, I get the definition, and if I hit generate, we get the definition, and that's the definition we want, because if you look closely at it, you'll see that it's sticking x onto. Thank you. Yes. So it's basically sticking. So you still have to look at this program to check it's doing the right thing. This doesn't free you from knowing what you're doing, but it does save you from doing the step that really the machine should be able to get itself. Should we test it? Do we do that? We could test it. It type checks, ship it. What did I call the program? Vectrans. I actually did. I did write a main program, so I can just give the size, and it'll. So this is compiling it and executing it. It's got some input that it's generated, and you see it transposed. Just for amusement, I'm going to show you how it compiles. It's kind of fun writing runtime systems, but sometimes you just want to make progress in your project. So this actually compiles via scheme, which horrifies everybody. And it looks a bit like this, so that's perfectly reasonable scheme, I think. That's perfectly. Anyway, what's really entertaining about this, though, I thought, okay, this is just a short-term thing, and I promise it is just a short-term thing. But yes, it is, honestly. What are you shaking your head for? So the amusing thing is, I did some little benchmarks of kind of made-up things of big merge sorts of lists, and ran it against original Idris, and this ran faster. Significantly faster. And then I ran it against GHC with optimizations, and this ran faster. And I just thought, that's ridiculous. This is scheme source code it's running. Who wrote this scheme compiler? Oh, Ken Dybvig wrote the scheme compiler. Clearly very good at this. So that's quite nice. Right, how long have I got? 4 minutes, including questions?
Sorry, about 9 minutes.
About 9 minutes. Okay, so I have one more thing I want to show, which is about tracking states in types. So just to bring it back to the thing that you might want to use linear types and quantities for safety. So it's my favorite introductory state machine. It's where I show you the door. I've shown people the door at this conference before, and not in this way. It's like I've done this like several hundred different ways now, I think. And now I'm doing it with linear types, because linear types are cool. So don't worry too much about all of the details of how this comes together. Definitely don't worry about this M, which stands for exactly what you think it does. But I've kind of defined a reference to an external resource, so the door, and a door has a state. The state is either closed or open. So my state machines in this example are significantly simpler than Hillel's were, but I suspect this scales up, and I've certainly scaled it up to slightly bigger things. And I've defined a few operations. I've only given the types because, well, this is just to illustrate what happens. So I can create a new door, and this one says, when you create it, there will only be one of it. So it will be using the one quantity. And when I say any here, it means the thing you create you can use as many times as you like. And there's a little bit of trickery in making this work as a kind of language you can program, a kind of DSL or embedded DSL you can program with. I won't go into the details of that trickery just now. Maybe sometime in the future, because I think it's kind of fun as well. But I'll just show you how it works, how it glues together. I'm going to write a program called doorprog, which is just it's like the type here says, you've got to return any unit. So all it really means is that if I use any of these operations to create a door, I have to end up in the right state. So you can kind of see a state machine here if you squint a bit. So I create a new door. If I knock on a door in the T state, it's still in the T state when it's done. I'll do close first. If I've got an open door, I get back a closed door. And notice this one says, I can only spend that door once. So once I've closed the door, I can't do anything with it again. I can only delete a door if it's closed. This is the were you born in a field rule. And this last thing, this open door, is a tricky one, because opening a door, like when we describe these state machines, it's kind of tempting to write the transition as if it always works. But it might be that like it's the door's jammed, say. And if the door is jammed, we might need to recover from the jam. Maybe we just want to try again. So we need to have some way of the system feeding back some information to us. So this res type it's kind of like a pair type. The first thing is the value it returns, and then the second thing is something that computes the state of the door based on the thing it returns. So this basically means if it returns true, then it returns door open. It returns an open door, and if it returns false, it returns a closed door. So this is another example of first-class types in action. If I want to do any kind of type-level discrimination on some value, I just write a function to do it. There's no difference between the two languages. They just write a function to do it. I'm not going to show you the definition of res because we're going to find it out in a moment. So I'll create a definition, and I guess this is only interesting if I create a door. So let's create a door, and we'll look at what we've got. So what have we got on the right in this bit? We've got an M that we don't talk about, so we're definitely not saying the M today. And we have a D, which is the closed door that we've created. So what can we do with a closed door? We can knock on it. If I try knocking on it, then and just doing nothing with the result, what have we got? Well, we can't use D anymore, and we've got this lamb. This is just I just didn't give it a name, so it's invented one. It's invented one that I can't actually use. This is an internal name. So if I want to make any progress, or if let's say I quit at this point, or let's say I claim that that's a valid use of the door protocol. Oh, my Vim short. I'm using I don't like to give away whether I'm a Vim or Emacs user, but I've just discovered a Vim editing mode for Atom, but it doesn't have all of my shortcuts set up, so I get confused occasionally. Let's try, just so you can see the error message. It says, this thing that we bound, there are no uses of it, so it's not a valid program. So we have to use it exactly once. It's maybe better if I give it a new name, so let's call it D prime. And it says, there are no uses of linear named D prime. So the only way I'm going to get out of this program now that I'm in is if I use that door in a valid way. Okay, so let's let's open it, just, let's call that res. Let's open the door, and let's put that hole back in. And my Vim shortcuts don't work. And let's put that P in there, because it's not important. But right, so if we check the type now, we see, right, we've got the result. This is the result of opening the door. I don't know anything about that result yet. I don't even know how res is defined. I could look it up, but I could also try case splitting on it and see what it tells me. So if I case split on it, it gives me, well, it tells me what that result is. So I've got a val and I've got a resource. And if I check the type of door prog right-hand side, it tells me you've got a val, which is a Boolean, and you've got a resource, which is a door that if val is true, then it's open. If val is false, then it's closed. So in order to make any progress on this, I have to do the dynamic check. Like I have a door, but I don't know what state it's in until I've checked what state that door is in. So I guess what I could do for that is pattern match on val, because val is, if I look at the types here, val is the thing that's blocking me from making any progress, so I'll split on it. So now in the case that opening succeeded, I have an open door. In the case that opening failed, I have a closed door. So I guess what we'll do is, I'll call it D prime, I'll close that door, and we'll see what we have. So we have an error. What did I spell wrong? Trying to use a because it's called resource. Huh. I'm going to call it D because I'm a functional programmer, so I use single letter variable names. Nobody laughed there. So I have the D. This is the D I had in the past, so we can still talk about the glorious days when doors were open. But we can only work with the modern times when doors are closed. So just to tidy up, because I don't want to leave my program unfinished, I will tidy up, I'll delete the doors, and check that it type checks. And it type checks, we'll ship it. I'll shut up, thank you for listening.
Got time for one question, so Miles.
Well, don't pick Miles, he's going to cause trouble.
Got a minute.
Maybe I am. This is absolutely lovely stuff. So looking at the quantity annotations, I'm sort of imagining if I can see myself using these things, and I can see these things sort of spreading throughout my call graph in sort of fairly viral kinds of ways. Have you experienced that playing with this stuff? Is it a problem? And if it is a problem, is there any way of being polymorphic over them?
So if you've seen the Haskell linear types system, it's very similar to this. In fact, I think I got some of the ideas of how to implement it from the Haskell linear types paper, and they have this idea of polymorphic quantity annotations. I've done something slightly different. In this example with the door, I've got a function that computes the correct quantity annotation. But I think you're absolutely right that we're going to have to think very carefully about library design, and are we going to end up in situations where we have a function that only uses a thing once, or always uses it exactly once, but it is not revealed to us in the type? And that's a very good question, and I don't yet have a satisfactory answer. But I'll have fun finding out, I'm sure. But thanks for the question. That's a really important thing to think about. Yeah. I knew he was going to cause trouble.
Yeah, thank you. Thank you, Edwin.
Okay, thank you.